This is Unit 2, Video 5, the last video of our unit, and here we'll talk about heating curves. Something called a heating curve. Now, a heating curve is actually a graph which has heat down below, so this axis should be labeled as heat, and then temperature on the y-axis in degrees Celsius usually, and it shows 5 distinct parts of the phase change as a substance goes from a solid to a gas. So down here, we're actually beginning as a solid. And up here, we're ending as a gas. Now these 5 distinct parts, notice there are 5 of them. 1, 2, 3, 4, 5. 2 of these are flat lines. So what you see here, the first flat line, shows you it's connected to a temperature, to 60 degrees Celsius. So this flat line actually represents going between the first 2 phases. So the first 2 phases are solids. This is a solid, so this must be the liquid phase. This third must be a gas phase. So as we go between a solid and a liquid, we call this melting. So this right here is actually melting. And the temperature that is shown on the left side is the melting point. So this is the melting point of the substance. So this substance melts at 60 degrees Celsius is the idea. The next flat line here actually lines up with 120 degrees, and this is called the boiling point of the substance. And it's pointing to this section, which is boiling. So what happens is, as you begin with a substance as a solid, what you do is you have to put heat into it in order for it to heat up. In this first, now this is a diagonal line, notice, the temperature is going up here. The temp increases in this section. Now, when we get to the melting stage, the temperature stops increasing. Notice it stays steady at 60 degrees Celsius. And then once all the molecules are melted, then we're a liquid. And now begin to increase the temperature of the liquid. In this case, what happens is the molecules are actually beginning to move faster and faster and faster. The molecules increase in their energy. Eventually we get to a point where the temperature steadies again, and we've passed from 60 to 120, 60 degrees worth of heating up, and then we're steady again. As we're steady here, the molecules are boiling. Here what happens is the molecules are flying apart. The bonds between the molecules are being broken, so now they're allowed to fly apart. And that's where we're becoming into a gas. And then in the last stage here, we're just heating up the gas. You can actually keep heating up the gas as hot as you want, just like you can kind of keep cooling the solid going this way. So these 5 distinct sections of the heating curve refer to the 5 different processes that we see here. Now, the question here is, why is the temperature staying steady during these phase changes? And if you think about this, let's think about boiling. So this portion right here. If you have yourself a pot of water, if you put a pot of water, say on a hot plate or on a Bunsen burner if you'd like, let's go ahead and use a hot plate, it's a little safer, and we allow the pot of water to essentially boil. So we'll actually get it to boil. So we got vapor coming off of it. We're going to stick a thermometer in here to check the temperature at which the substance boils. So here's our thermometer. And as we're heating it up, the temperature is going up, 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 up. Eventually, the temperature reaches 100 degrees Celsius for water, for example. And as the water boils, it'll probably take a good 30 minutes or so, maybe even 40 minutes, for the water to boil out. The question is, will the temperature change? And the answer is no. During this whole time, the temperature will actually stay steady at 100 degrees Celsius. And that's kind of strange, but it's true. Once all the water's boiled out, then the temperature will kick back up again. But it'll stay steady during the boiling process. The energy is being put in. We're not turning off the hot plate. The energy is actually going into breaking the bonds. And that's the idea, because this is an endothermic process. We are breaking bonds between the water molecules. And same thing with melting. When it's melting, if you stick a thermometer, if you do the same experiment except with ice cubes, you got some water, you got some ice, until all the ice cubes are melted, the temperature will stay steady. And it'll stay steady at 0 with, in the case of water. Here we have a different substance, so it'll stay steady at 60. That is the heating curve. Now let me show you one little detail about the heating curve, and that little detail will be right here. This is called superheating. And a substance, if heated very slowly, will actually increase above the boiling point, and then it'll suddenly decrease and start boiling. A very similar thing will happen with the cooling curve, as you'll see. So we'll demonstrate this through some videos to you in class. It's called superheating. Alright, so the second curve is the cooling curve. Now the cooling curve actually is the same thing except backwards. So here we're beginning as a gas at the very top, and we have to cool the gas until it becomes to a certain temperature. Then we're going to condense. So in this case, this will be called condensation. Once we've condensed, we've got a liquid. We're going to cool the liquid down, and then we're going to freeze. So this will be called freezing. Once you freeze the substance, it becomes ice in the case of water, and just gets colder and colder and colder. So we still have the five parts, except they're backwards. This is a liquid, and this again will be a solid. Now you'll notice that the temperature at which condensation happens is still 120. Whether you boil it or condense, it'll be the same temperature, and same thing here in the case of freezing. It'll still freeze at 60 degrees Celsius, just like the substance melted at 60 degrees Celsius. And the temperatures will stay steady. Now, let me show you something. In this case, what will happen is you can supercool. So what you can do is actually see a little dip, just like we saw it earlier. This is called supercooling. And this process is very cool. That's what we call it, supercooling. You can actually get the liquid to go below 60, to go down a lower temperature, and then all of a sudden it'll kick up and start freezing. We'll show you this process in class as well. So make sure you can interpret these two curves. This here should say heat would increase to the right, to the left in this case. So heat increases this way. More heat or less heat. Right, so let's finish up with this example problem. And it says, tell whether heat is absorbed or released by the molecules during the following phase changes. So we have ice cubes form in the freezer. So we put a bunch of, I guess we got an ice tray in which we're going to put some water. Now, in this case, what we have is we have water going from a liquid to a solid. Now ask yourself, are the molecules speeding up or slowing down? In this case, liquid molecules are actually moving past each other. They have some motion, right? They can actually move past each other. Solid particles, however, are stuck to one another, and they have only vibrational motion. They can't slide past each other. So they have slowed down. This process is slow down. The particles must slow down, and as they slow down, do they lose or do they gain energy? Well, to slow down, they must lose energy. And as they lose energy, this is called exo or endo. It's actually called exothermic. Because exo means out of. Energy is actually released. Energy is removed as this happens. So this is an exothermic process. Here it says liquid butane becomes gas as it leaves the lighter. Now, if you've ever seen, most likely you have, a little butane lighter is usually, you turn it on, and what happens is the substance inside is a liquid. Now, if you don't get the flame to go, if you just release some of the liquid butane, it actually becomes a gas. So here we're going from a liquid to a gas. Ask yourself the same question. Are the molecules speeding up or slowing down? Well, in a gas, the gas particles are actually speeding up because they're moving much, much faster than liquid particles. Liquid particles can kind of hang out and touch each other. They are moving, but not as fast as the gas. So again, in this case, particles are speeding up. Now, if they're speeding up, that means energy is released or absorbed. Well, in this case, the energy must be absorbed. The particles need energy to speed up, so energy will actually be absorbed. In this case, so they are speeding up. So energy is absorbed. If energy is absorbed, we call this endothermic. Now, usually, without having gone through this little explanation, students get it backwards. So be careful, make sure you think. I want you to think through whether molecules are speeding up or slowing down, and then to speed up, do you have to absorb or release energy? And that's how we find out that this is endothermic. All right, go ahead and try one on your own. Go ahead and pause the video, try this on your own. And we haven't talked about sublimation in terms of absorbing or releasing energy. Well, In sublimation, remember, we are going from a solid directly to a gas, bypassing the liquid state. This happens famously with a substance called dry ice. Dry ice is actually called dry because it's a chemical that bypasses the liquid state. That's why they call it dry ice. It's oftentimes used in Halloween decorations and stage decorations, and usually you'll see it in chemistry, used in chemistry. But because this is bypassing the liquid phase, it's still going from a solid to a gas. So you have a solid, particles again are close together, and they're not moving past each other. In a gas, particles are very far apart, moving very, very quickly. So a lot of energy has been absorbed. Energy must be absorbed in this case. So this is actually very endothermic. And endo means heat is pulled into the molecules as this happens. This is why it's very dangerous not to touch dry ice with your bare hands, because as you put your hand on it, it'll absorb all your heat and give you frostbite. This is a very endothermic process. Again, endothermic means energy is absorbed. All right, this finishes the chapter for us, Unit 2.